hopefully you can help us. Okay, let me just recap what we were talking about. We were talking about this result that if we have y, which is distributed like a canonical Gaussian vector or Gaussian distribution, which means it's a normal distribution or has a normal distribution with mean 0 and covariance identity, then y transpose py, which is also equal to py norm squared. This has a chi-squared distribution with r degrees of freedom if this P matrix is a projection matrix whose rank is R. So the key here is that P should be a projection matrix, and the rank of the projection matrix appears as the degrees of freedom. Okay, and there was an alternative characterization of this results where you could say X has normal, is distributed like a normal distribution. It means 0 and covariance matrix P. Then the norm of X would have chi-squared with R degrees of freedom. Okay, so and then there was this example that we went through. We can use this result to show that the norm of E squared divided by sigma squared has chi-squared distribution with degrees of freedom being n minus d. So this is the degrees of freedom of I minus h, which is a projection matrix. Okay, so now we wanted to go through the proof of this in this lecture. So now let's go back to Jake. So let me ask again, is anyone else look at the proof besides Jake?
I got a chance to look at it slightly too.
Okay, great. So maybe we'll go with both of you guys. So maybe Jake first. Do you want to? Was it clear? Was there any specific part that?
I think I understand it mostly.
Okay, so do you remember how to, like, if someone asks you to prove this, how do you?
So do you want me to start with the proof that ytpy is equal to the norm of py squared, or just hop into proving that it's given by chi r squared?
Yeah, that one we already discussed last time. So what I want to show is proof of this fact that this implies that y transpose py, this and the fact that P is projection, is a projection matrix with rank P equal R, then this would be distributed like chi-squared with R degrees of freedom. So what would be the
so the first step would be expanding out the norm squared of py into the spectral decomposition with u lambda ut.
So there's no norm here, right? So we have this, right? Mm-hmm. So what do we expand here?
Well, we proved that that's equal to the norm of py squared.
Okay, that's fine. Okay. So
then we split P into the spectral decomposition, which is U lambda UT, because it's we can do that because it's orthogonal.
We can do that because P is orthogonal?
Yeah.
But P is not orthogonal. P orthogonal means like P is identity.
U is orthogonal, and then because it's just spectral decomposition, and then the middle matrix is going to be diagonal.
Yes, okay, that's fine. This is correct. This is orthogonal, this is diagonal. The reason that we can do this is because this is P is symmetric, right? It doesn't have to be orthogonal. And in fact, so do you remember what an orthogonal matrix is? So what is an orthogonal? Maybe Kaylee, do you want to? So U being orthogonal, what does it mean?
It's a matrix where it's a square matrix where the columns and rows are orthonormal vectors.
Okay, good. Columns
Right.
and so square square matrix where the columns and rows are orthonormal. So if we want to write it in matrix form, what is an equivalent statement in terms of, let's say, U and U transpose? There's a relation that they satisfy together.
UTU is equal to UUT, which is just the identity matrix.
Okay, great.
And then the
so this
inverse is equal to the transpose.
Yeah, so this is equivalent to the inverse of U being U transpose, or the inverse of U transpose being U. Okay, great. So, and then if you expand this, for example, being equal to identity is equivalent to the columns being orthonormal. And this being equal to identity, I believe, is equivalent to rows being orthonormal. So if you write U in terms of its column expansion, I think we had done this in the discussion of gram matrices, if you go back to that slide. So if you write it as this, then you'd recall that U transpose U is just a matrix whose entries are basically the inner product. And so when you say that this is identity, it means that all the off-diagonal entries are 0. So the pairwise inner products are 0. So the pairwise orthogonal, and then diagonals are 1. And diagonal is just the inner product of UI with itself. Okay, this is good. So just to make sure, so P is a projection matrix. Projection matrix. Is it orthogonal? Is P itself orthogonal?
P itself is not orthogonal, no.
Why not? How can we show that it's not orthogonal? So I can try to compute P transpose P and see if it's identity, right?
And
Yeah.
that wouldn't be equal to the identity because it's idempotent, so that's just P squared.
Right? It's symmetric first, it's P squared, and then idempotent means
P.
Yeah, so this is going to be P. So it's orthogonal in a very special case. It's orthogonal if and only if P is equal to what? There's a very special case in which it is orthogonal, otherwise it's not. If P is the identity matrix. So the identity matrix is a projection matrix. It's a trivial projection matrix. So that's the only projection matrix which is an orthogonal matrix as well. Okay. So P itself is not, in general, let's say if the rank is less, so if this R is equal to N, so this is the only projection matrix whose rank is equal to the dimension. So rank is N. If the rank of the projection matrix is strictly less than N, then it can be identity. And so it's projecting onto a proper subspace of Rn. And so this identity is true, but this side wouldn't be identity. So that would violate. So good. So let's say in general, P is not going to be orthogonal, but it's symmetric, and every symmetric matrix has this decomposition. Okay, and then you recall what these are, right? So what is the relation of these U's and lambdas to the matrix P or the eigen decomposition? You remember these, right?
The eigenvalues are going to be on the diagonal of the diagonal matrix. And since it's a projection matrix, the eigenvalues have to be 1 or 0.
Okay, great. Right.
Do you want me to keep going or?
Go ahead, yeah.
I was just going to say, and the number of ones is going to be equal to the rank of the projection matrix, which is going to be equal to R.
Okay, great. So this is a lot of information. So lambda is the diagonal of, let's say, lambda 1 up to lambda n. And these are the eigenvalues of P, and then lambda I are either 0 or 1. So did you guys remember? I believe you proved this in one of the homework problems. So true for any projection matrix. And it's in fact a consequence of this. Do you remember the proof? Anyone remembers how you proved this? Jake, maybe? Kaylee, others? Yeah, go ahead. One of you guys. How do you prove it? Now that you know this, at least let's try see. Anyone recall? So suppose I start from P transpose equal P squared equal to P, and I plug this in. What would I get? I get U lambda U transpose squared equal U lambda U transpose. So now, does this simplify? Am I still on? You guys?
Yeah,
know?
it simplifies to U lambda squared UT.
Okay, U lambda squared UT. That's a property of the orthogonal. I mean, if you're not seeing it, just expand it. This multiplied by itself, and then for orthogonality to simplify. So now I have this relation. So does this simplify?
That shows that lambda squared is equal to lambda.
How is that? I mean, how is that? I mean, how does that follow from this?
That only happens when the eigenvalues are 0 and 1.
Yes, this is true, but let's say why this implies this. So what you would do is multiply from this side and from this side by U transpose and do both sides of this. So you'd multiply like this. You can do it once for this, and then once for the other one, and then these would be identity. Okay, so try this out. So this follows, and then this is just saying lambda I squared is equal to lambda I, whose solutions are either 0 or 1. Okay, so that's the proof. Okay. Okay, what else? So I guess Kaylee also mentioned, I think, okay, so the number of eigenvalues that are 1 is equal to the rank of P. Okay, so how do we show this? Or maybe argue why this is the case? There's a more general statement. So how does the rank of a matrix relate to its eigenvalues? Say a symmetric matrix. More generally, rank of P is equal to the number of ... eigenvalues of A, let's say a symmetric matrix of A. So what should we put here? In place of the dots. Distinct. That's not going to work. Distinct. So for example, if you look at the identity, identity has all the eigenvalues the same, but it's full rank. So you have to try something else. Anyone else? Just like make another guess. Eigenvalues. No other guess? So this would be non-zero. So the number of non-zero eigenvalues of A is equal to the rank of A. And there are different ways of showing this. I'll let you think about it. So in this case, once you like rule out zero, the only non-zero eigenvalues are ones. So it's equivalent to saying that the number of eigenvalues that are one is equal to the rank of P. Okay. So this is great. Now let's like move forward with the proof. Maybe Jake or Kaylee, one of you guys, what should we do next? So I have this, and I know a lot about the eigenvalues. And then, by the way, the columns of this would be the eigenvectors associated with those eigenvalues. That's also good to know, although we're not going to use that in this proof. So what's the next step?
We could just plug that into the norm of py squared. So it'd be u lambda ut y. And then from there, we need to define a variable z in place of uty.
Okay, let me do this. You plug this in, okay, and then define a new variable. This is z, right? Was that?
Yes.
Okay, okay. So next.
And then from the properties of unitary invariance, this is just equal to lambda z, the norm of lambda z squared.
Okay, so this is just u lambda z, and then this is equal to lambda z. So what is that unitary invariance that you mentioned?
It's just a property where it's like it's the norm of ux squared. It just reduced down to the norm of x.
So is this true for any u or a special u?
Is it just for square ones, or?
Is it for, no, this should be more special.
Oh, or is it just because it's orthogonal?
Yes, okay, this is great. So orthogonal matrices are, so orthogonal is a little more fancy name is unitary. A unitary matrix is like a complex orthogonal matrix. So instead of transpose, you do conjugate transpose. And so if you're working in reals, or unitary matrices are orthogonal matrices. So L2 is called unitarily invariant, which is to say that it's invariant under transformations by unitary operators, or unitary matrices. In other words, orthogonal matrices. And how do we show this? You'd expand this side and use the fact that U transpose U is identity. Just do it and it follows. So this shows that if you think of matrices as transformations, so it transforms, you transform X by this. These are linear transformations. So this transformation preserves the length. So the length of the transformed vector is the same as the length of the original vector. So that's why they're sometimes called unitary, or they're not. That's not why they're called unitary. So they're isometries basically, in the sense that they preserve length and also angles and preserve geometry of the space. Okay, that's a little bit more than we need, but so unitary invariance of, I'm going to say L2 norm. So the norm that we've been looking at is the L2 norm. We haven't looked at any other norm, but there are other norms possible, and those are not unitarily invariant. But the L2 norm, which is the norm that we have been working on or working with is Unitarian ring. Okay, so great. Now what? Any questions so far? Is this? I'm assuming that if you're not asking questions, it's clear. Questions? So what's the next step then?
To expand out the norm squared of the lambda z into lambda z transpose lambda z.
Okay, lambda z transpose lambda z. Okay.
And then that just simplifies to z transpose lambda squared z.
Okay, lambda transpose lambda z, and these are the same, so you get lambda squared. Okay. Lambda is diagonal, so it transposes itself. So now what? So this is actually a quadratic form. Yeah, you can see that this is a quadratic form with in the z and matrix lambda squared. So we have reduced the problem. Remember, a general quadratic form looks like this. And I have z here, lambda squared, and z. So lambda squared is diagonal. So we have turned the problem, which was this, for a complicated matrix, to a problem in which the matrix is diagonal. That's the main purpose of the spectral decomposition, U lambda U transpose. Using that, you can translate things for general matrices, general symmetric matrices, to diagonal matrices. And that simplifies a lot. So now, so yeah, go ahead, Jake. So Z transpose lambda squared Z, how does this simplify?
Well, that's just equal to the summation up to n of lambda I zi. But since we know the lambda i's are only 1 or 0, it could just be reduced.
So wait a little bit. So this is going to be lambda I zi, but that's not the case. It's like something is missing.
Squared, zi squared.
Okay, how about lambda I?
Well, lambda I is just 0 or 1, so.
Okay, right. Yeah, fine, that's okay. In general, it would be lambda I squared, because the elements of this are going to be lambda I squared. It doesn't matter in this case, you're right. But it's just worth remembering, like noting that. So in general, the reason why this is the case, if you believe this formula, you can see if A is diagonal, these every term that is coming up from the multiplication of pairs of different I and j's would go away, because that would be 0, and only the terms in which I is equal to j remain, and so you'd get ai yi squared. So that's what happens to a quadratic form if you have a diagonal matrix, and this is exactly happening here. And so as Jake pointed out, there's like a simplification you can also make. So I'm gonna maybe write this back down there. So just do this for yourself. So this is going to be summation I from 1 to n lambda I squared zi squared, which is also equal to lambda I zi squared. So then what was the last step?
We can reduce this down to just the sum up to r of zi squared, because it take the 0 eigenvalues, just we can ignore them, and the ones just are constants.
Okay, yes. So we should point out that at this point, so you can reorder eigenvalues any way you want, as long as you order the columns of this accordingly. So we have to say that first, you order the eigenvalues so that the ones appear first. You could just like rearrange in any order that you want, but it's like common to put the larger ones first and zeros there. So if we do this, then lambda 1 up to lambda r would be, so this is lambda 1 up to lambda r would be 1, and then the rest would be 0. Then I can set, this is exactly what we get. From 1 to r, we get lambda I equal to 1, and the rest is 0. Okay, so then what?
Then we're almost done, because we just need to find the distribution of Z, and which is again
Okay.
just going to be standard Gaussian. So this is sum of standard Gaussian IIDs, which is just the definition of chi-squared.
Okay, so we know, I'm going to come back to this. This is, can you say that again? What is this distribution?
This is standard normal, 0 in the identity matrix.
Okay, standard vector Gaussian. Okay, this is, so which means that the entries are, what do we know about the entries?
They're IID.
Okay, they're IID from a standard normal. Okay, and then what would happen?
And just by definition of that, in the chi-squared, we're summing IID standard normals. So we're done with the proof.
Okay, great. So by this definition, we're summing squares of IID standard normals, and we have R of them. So that by definition has a chi-squared with R degrees of freedom. Okay, so that finishes the proof. But what about this? So let me ask someone else. So anyone wants to argue why this is true? This is also a key piece here. We know the distribution of Y is given like that. Y is distributed like normal with mean 0 and covariance identity. How about Z? Y. Maybe Kaylee or someone else who has looked at, or just, you don't even need to look at this. At this point, you should be able to drive. So I know the distribution of Y. What is the distribution of U transpose Y?
For the covariance part, so that we're proving that it's the identity matrix, it would be U transpose covariance of YU.
Right, okay, so this is from the formula, like A covariance of Y, yeah.
And then that ends up simplifying to U transpose U, and we know that that together is the identity matrix. So,
right, okay, good. That's from the, from this orthogonality sort of assumption.
yeah, since U is orthogonal.
Right, okay, so we have the covariance. The mean is also going to be simple. So the mean is U transpose Y, right? So this comes out by linearity expectation. So the mean is 0. The covariance is identity. So why this is normal? Why can I say that the distribution is, let's say, multivariate normal? This is saying more than these two statements, that the covariance and the mean are given by these expressions.
Is it just because it's an affine transformation, so you know it stays
okay,
normal?
Great. Yeah, so it's an affine transformation of Y. In fact, it's a linear transformation. And so we know affine transformations are of Gaussian vectors are again Gaussian or multivariate normal. Okay, good. So we actually are done with the proof. So you can see there are many interesting sort of ideas that are coming into play. None of which by itself is like difficult, but when you put them together, you get a very interesting result. So we use the fact that for a symmetric matrix, we have this spectral decomposition where this is orthogonal, this is diagonal, and this allowed us to reduce via the unitarily invariant sort of nature of the L2 norm, allowed us to reduce the problem to a quadratic form, which is, or whose matrix is diagonal. And in a new random variable, which is, this is also a unitary transformation of Y. U transpose itself is orthogonal. You can verify once U is orthogonal, U transpose is orthogonal because this definition is symmetric. So a matrix, once it's orthogonal, the transpose is also orthogonal. So this is an orthogonal transformation or unitary transformation of Y. And this is sometimes called like rotation invariance, or you can say your unitary invariance. unitary invariance of the Gaussian distribution. So the Gaussian distribution, like the L2 norm, is unitary invariant. So if I have a random variable, apply a unitary or orthogonal transformation to it, if it's the canonical, not any, if this was the general sigma, this wouldn't be the case. It would be still Gaussian, but the covariance would change. But if I start from the identity covariance matrix, and if I have a Gaussian like that, then this distribution is invariant under orthogonal transformation or rotation. So these orthogonal matrices generally rotate or reflect the space. So under the rotation of the space, or the general orthogonal transformation of the space, the distribution does not change. And you can imagine if you plot the level sets of, you can see like if you have seen the Gaussian, bivariate Gaussian, these are the level sets. It's like a, if you plot the density, it's just symmetric. And if you rotate this space, if you look from either direction, it looks the same. There is no, if I rotate this whole plane, none of the distribution, nothing changes in the distribution. So that's why it's called rotation invariance, or unitary invariance. Okay, so we use that fact about the L2 norm and about the Gaussian distribution, and also the fact that once you do the projection, for projection matrices, we have these properties of the eigenvalues. So the eigenvalues are either 0 or 1, and they're exactly R of them if the rank of P is R, and then you're done. So I encourage you, if you haven't gone through the proof, go through the proof yourself and then verify everything. And if you can verify everything, then you know a lot about this course. So all the little pieces that we discussed sort of come together in this proof. Okay, questions, comments? Okay, so this is good. There's another result, which is, okay, so this is an exercise I'm gonna skip. You can show, for example, that if you have a normal random vector, if you take y bar and then square it multiplied by n, this would be chi-squared with 1 degrees of freedom. So this might not look like a quadratic form the way we have it, but I mean, this exercise goes through it. You can write it as y transpose ay for a projection matrix, a rank 1 projection matrix, which is this guy. You can verify that this is a projection matrix by seeing that it's symmetric and idempotent, and you have to verify that's rank 1 so you can compute the eigenvalues. Once you compute the eigenvalues, there's only one eigenvalue of exactly 1, and the rest are 0. So this is rank 1, and so this y transpose ay is going to be chi-squared with 1 degrees of freedom. So this is a good exercise for you to go through. I'm going to skip the details. The next result that we need from this discussion of quadratic form to be able to prove. So recall that we use this result to already prove something which we have left unproven. This was the result, and this allows you to drive the T statistics. So you know that the distribution S squared is basically a rescaled version of this, and from that we get the T distribution and so on. However, this result is not enough to find the distribution, that additional sum of squares that we need for the F test. So we need another result, which I'm not proving here, but it's called Cochran's result, Cochran's, or I believe it's Cochran, but it might be pronounced differently. So that's this result. So anyone got a chance to look at this result?
I took a little look at it, but I got lost about halfway through the proof you showed.
I don't think I proved this. Did I prove it in the? Maybe the proof of the other result, right?
Yeah, the proof of the other result.
Right. Okay. So what is the statement? So do you get the statement of what this is? What the Cochran's theorem is saying?
It's saying that if we know one quadratic form is given by let's say R degrees of freedom, then Q1 would be given by R minus R1, right? And Q1.
Right. The setup is a little bit more, let's say, subtle. So first, what are the relations of these? So we have to set the problem properly and state what is known about these quadratic forms and what not, okay? So the setup is we have a quadratic form Q that can be decomposed as the sum of the other two. So what this is saying is that I can write, I have like Y transpose AY, and this can be written as Y transpose A1Y plus Y transpose A2Y. So the idea is that I can write this for any Y. In quadratic forms are functions of Y. So no matter what I take Y, this is going to be the case. So this we call QY, or Q. This is Q1, this is Q2. So we have such a decomposition that holds for any Y. Should hold for any Y. Okay, that's the first assumption. So then what? Then what is Cochran's? So first assumption is this decomposition. Then
is the second assumption just that Q1 and Q2 are independent?
No, that's actually a conclusion of the theorem. That's the interesting thing is that this is not assumed. This follows from Cochran's theorem. We don't know that Q1 and Q2 are independent. See, the assumptions are actually listed here. So all that we know are these, that this has a chi-squared distribution with R degrees of freedom, this Q. This has chi-squared with R1 degrees of freedom. And that this guy, we don't know the distribution, but we know that this is non-negative. Okay, so we have the decomposition. And then we know that these are true. Then the conclusion is that these two pieces have to be independent random variables. Okay, all of them are random variables. So because Y is random, these are all random variables. The conclusion of the Cochran's theorem is that Q1 and Q2 are independent. Furthermore, Q2 will have a chi-squared distribution as well. And the degrees of freedom would be R minus R1, which we're calling R2. So as a consequence, it follows that this has to be non-negative. So if you have these conditions, R1 has to be less than or equal to R. Generally, it would be strictly less than R. It can't happen because otherwise this doesn't make sense. So as part of the conclusion, I'm not assuming that this is less than this, but it follows from the Cochran's theorem. Okay. Any questions?
Can you go over one more time why we can conclude that Q1 and Q2 are independent?
I'm not proving it. It's just the result of the theorem.
Okay.
It's not obvious. It's not at all obvious. This theorem is not obvious, and I usually don't prove it. We can at some point prove it if you guys are interested, but this is actually an interesting part of why this is a theorem. Otherwise, it wouldn't be called a theorem. It's not at all obvious why they would be independent. Yeah.
Yeah, I just wasn't sure if there was some intuition behind it without going into the full proof.
I don't have a good intuition. It's just a surprising fact, in fact, and it follows from once you go through the proof, which I don't have the proof here, but once you go to the proof, that would become rather clear. It's not obvious, and I don't have an intuition, unfortunately.
No worries, thank you.
This is an interesting fact about quadratic forms, and this is the basic building block. It's non-intuitive and non-trivial. It's one of the more non-trivial, one of the most non-trivial results that they get these in this course. I'll try to see if I can, maybe next time if you guys show up, I'll show you. I'll see if I can find a good proof that I can present we're a little bit ahead of time, so I might like this time prove it. But let's accept this for now, and then try to use it. Okay, so suppose we know this. This is the only thing that's left unproven in this course so far. There's an application of this, which again, I'll encourage you to go through. So you can write, for example, summation of yi squared as this plus that. And you know that this is chi-squared with n degrees of freedom. If this is the case, this is from basic definition. This you proved in the previous exercise, that's chi-squared 1. And you notice that this is not negative. Then Cochran's theorem tells you that these two terms have to be independent. Furthermore, this will have a chi-squared distribution with the degrees of freedom being the difference between the degrees of freedom of these two, which is n minus chi-squared with n minus 1 degrees of freedom. So this proves that this is chi-squared with n minus 1 degrees of freedom, which you might have seen in previous courses. But this is a proof of, like, simple proof. You can also write this directly as like y transpose I minus 1 over n1, 1 transpose times y. And this was a projection matrix. This is going to be a complementary projection matrix. So you can use the previous result that we had. You don't need Cochran's theorem. If you're interested, you can do it directly via that, but Cochran's theorem also gives you. There's also a general version of the Cochran's theorem where you have like multiple quadratic forms here on this side, and you know the distribution of everything except the last piece, like one of the quadratic forms on the other side, but you know that that's non-negative. Then the conclusion is that all these quadratic forms on the other side would be independent, which is very strong conclusion. And the last piece, that whose distribution you don't know, will have in fact the chi-squared distribution, the degrees of freedom of which being the difference between the degrees of freedom on this side and the sum of all the degrees of freedom of the terms that you know on the other side. So we're not going to use this version, but it's good to know that it's there in case you need it some point. Okay, so any questions about the setup of this? Besides the proof, which we haven't discussed. So let's see how we can use this to prove. Oh, it's not here. I guess we have to go back to these slides. And so that actually is the proof here. So so we call the theorem that we had, the basic one that everything is based on, the F test, is that if I have regression and if I project, I have two subspaces, one L of x, which is the image of x. That's the space in which this x beta lives without any restrictions on beta. And I have A of x, which is the restricted subspace. So beta has some constraints satisfied. So that's x beta, all the x betas for which beta satisfies the constraints under the null, these guys. Then I have these two projections. And once I have these two projections, I take the difference, and that would be my and then the square, take the norm and then the square, square that term, that would be the additional sum of squares. So this result is staying under the null. This divided by sigma squared has a chi-squared with q degrees of freedom. And furthermore, this is independent of that. And you can see like how maybe Cochran's is coming in. Cochran's is actually giving you this independence. So this suggests that these are pieces of that a general quadratic form. So you have a decomposition of quadratic form in terms of these two, and the Cochran's is giving you independence, which is exactly what happens. Okay, so let's see if you guys can help me connect this to, maybe I'm gonna do the proof above it so that things are not messed up. Okay, maybe, I don't know, one of you guys who have gone through the proof, maybe help get started with this.
don't we just start with the fact that the norm squared of E plus the norm squared of the mu alpha, or yeah, plus the norm mu alpha minus mu is equal to the norm of EA squared?
Okay, yes, great. So we start with this Pythagorean identity, which again, we can prove in different ways. Geometrically, it's clear. So this is saying E, and then this guy, and this form a triangle with right angle. It's easy to drive because mathematically you can prove it, because you can write EA is equal to, so remember, mu hat is y minus basically EA, or EA is, sorry, E, or E is basically, let me write it the way that you guys are more familiar with. So E is y minus mu hat. EA is y minus mu hat A. So I can write EA is equal to, in fact, E plus mu hat minus mu hat A. You can see if I add this to this guy, I get back this, okay? And then we know that E is orthogonal to mu hat minus mu hat A. The reason being this entire thing is in the image of X, which is L of X. So just argue for yourself, and you know that E should be orthogonal to the image. So these two pieces are orthogonal, then the Pythagorean theorem says that when I square this, the cross term goes away. So if you expand the square here, if you have yet two vectors where X is orthogonal to Y, then this is going to always be. You can use algebra to prove it, because there's going to be a term in general 2xy, and this would be 0.
Professor?
Yes.
So EA is E minus mu hat plus mu hat A, right?
You mean minus here?
Yeah, and plus mu hat A, UA hat.
So is this correct? Are these? If that's correct, then what I'm doing here is, like, let's say plug in here y minus mu hat, right? Then this would cancel out, and I get y minus mu hat A, which is this.
Oh, okay. I'm sorry.
Right.
Thank you.
Okay, no problem. But it doesn't matter, even if it was like negative of this identity doesn't change, right? But this is an algebraic proof. Like geometrically, it's also clear. But in order to prove it, you can use that. So these two together show as an exercise. Okay, so we have that identity. So what is next?
To divide it all by sigma squared.
Okay, so we're going to divide everything by sigma squared. Or I put sigma in there, or they can divide it by sigma squared in there as well. So what is the next step?
Here's where I got a little lost, but we know that the first term on the left side of the equal sign is given by chi. This is basically in the Cochran's form. So
right.
we both know that, yeah. So we know that the EA over sigma, that's going to be given by chi squared. And we also know that the E over sigma is chi squared.
Yeah, both of them would have chi-squared distribution. But first we have to argue that these are quadratic forms in terms of something, right? So we have to say that these are actually quadratic forms. How can I argue that they're quadratic forms?
would we just do it in a similar fashion to how we like in the first proof we did today?
I don't want to explain. I'm not. Yeah, I just want to say that this I can write, for example, as like y transpose. For some vector y, I can write it as y transpose ay. That's what I want to show. Not necessarily, I don't want to make it into like a diagonal matrix or anything. To see that this is a quadratic form, we just have to notice that how does this relate to y? How can I get the residual from y? So let's say for E, let's do it for E. If you recall, this is like I minus h times y, where this is the projection onto the image of x. And for EA, I can write the same. This is also a regression problem. There is a projection associated with that restricted progression. If this is projecting onto LA of x, and so I get something like that. Then you can argue that yes, so this is like a quadratic form. This is like, for example, this is I minus h ay, and this is similar. So y is so there is a problem here. So let's say if we did this, so y is normal, which means 0. It's not 0. So the mean of y is normal with mean mu, and this is sigma squared in. So I can write it like that. There's also the epsilon. So you know that we know that basically y is mu plus epsilon. Epsilon is, this is x beta. Epsilon is normal with mean 0 and covariance sigma squared in. So this is good because the mean is 0. Y, however, has in general a non-zero mean, right? So I want to write things like, I want to say that this is p times y. We know that this is a quadratic form. If this is a projection matrix, maybe that's what you meant, right? Okay, so something in the chat. Rank of I minus h. Yeah, so we get to the rank of I minus h. I just want to first mention how do we write this in the quadratic form, like appropriate for the Cochran. I can write it like this. So you know that, for example, so what is the distribution of y divided by sigma? If I know this, I'm just going to say it. It doesn't matter because we're not going to use it. So it's going to be mu divided by sigma, and this is going to be in. Okay. So if I look at this, this is the covariance is right, and this is a projection matrix. So this is like p times y. However, the issue is that there is a non-zero mean here. I want this to be a vector, Gaussian vector whose mean is 0, so that I can apply that result, because that result says that this has to be 0 mean. Otherwise, the distribution, in fact, is not going to be chi-squared, but it would be like non-central chi-squared. So what should we do here? So is there a better representation that we can do? What can we do about this non-zero mean here? Do you see the issue? So let me help you. What we are going to do is that we're going to say that we can actually write this as I minus a h times epsilon, and then over sigma. So I can replace y with epsilon, and epsilon has 0 mean. It has the right, because then epsilon over sigma would have a normal, which means 0, and covariance identity. And this is exactly what I want. This is like a P matrix projection, and this has the right distribution. So this would be a chi-squared. This would be a quadratic form. First quadratic form. This is also a quadratic form in y, but the distribution is problematic I mean, we can't directly use the result because we don't know what happens to this mu. However, it turns out it's equal to that, and this we know is chi-squared with rank I minus HA as its degrees of freedom. Okay, so why can I write this as that? Anyone? This is the tricky part for this proof.
I'm a little confused on why. How can you just replace the y with the epsilon term?
That's what I'm asking, actually. That's exactly the question. Why we can do that. In fact, you can show that this is true. This is equal to I minus HA times epsilon. Under the null. This is not always true, but under H naught, under H naught, mu is in LA of X. Okay, so under H naught, assuming the mu is in LA of X, this identity is true. So the question is that why is this true? So I minus HA times y is in fact I minus HA times mu plus epsilon. So I get I minus HA, this is times mu plus I minus HA times epsilon. What I'm claiming is that this term is 0.
Is that just
Question.
because it's in the image of LA of X?
Great. So you say mu is in the image of, it's actually in LA of X. That's we're not like having a matrix whose image is this, just in there, and then HA just projects onto that. So HA of mu is equal to mu. Since mu is in there, HA of mu is mu. This is like assuming that the mean, remember the mean is inside that subspace, the restricted subspace. And so when you project to bigger space or to smaller space, you always get back the same thing. And in this case, if I project mu to LA of X, I get the same thing. And so this would be, this is the projection onto the orthogonal complement, which is 0. Or you can say you get mu minus HA mu, and mu, HA mu is mu. Okay, so this is only true if mu is in the LA of X, which is true in the under the null. Okay, under the null we have that identity. Is this clear to people? That's the key point in this proof. There's another point, which is also that similarly for this, I can say that I can write this as I minus H times y divided by sigma, or I can also say that's I minus H times epsilon divided by sigma. Why is that? So we have HY is basically H times mu plus epsilon. And, or I minus H. Let's say just, you can fill in the details, but what we need is I minus H times mu is 0. So we know that I minus HA times mu is 0. Why I minus H times mu is 0? Anyone? This one is in fact true both under the null and under the alternative. As long as the regression model holds, you know that mu is in L of X. Right, that's the assumption. Or this is just the image. That's the regression assumption that y can be written as x beta plus epsilon. You know that mu is like x beta. And so mu is in the L of X. And so when you take the this is like h implies that h mu is mu. And so this would be 0. So try to argue that for yourself. Mu is always going to be in L of x. The projection of mu onto the L of x would be the same as itself, because that's the assumption of regression. That the regression is assuming that the mean of y is in that linear subspace. So now what we get is this is a quadratic form in epsilon. This is also a quadratic form in epsilon. Both of these, we know this is also going to be q chi-squared with rank I minus h from the result that we had just proven in this lecture. So this is chi-squared with a certain number of degrees of freedom. This is another quadratic form with chi-squared distribution. And so, and then we have this decomposition, and this is non-negative. We also know that this is non-negative. So all the conditions of the Cochran's theorem are satisfied. All the conditions of the Cochran's are satisfied. So note that both of them are quadratic forms in the same variable, epsilon. And epsilon over sigma. And epsilon over sigma has this distribution, which is what you want. This is like replacing y in that theorem. So this implies that, so if I call this q, call this q1, call this q2, this implies that q1 is independent of q2. So this additional sum of squares, this is independent of q1. That's exactly this conclusion. Because dividing by sigma squared doesn't matter. So if these two random variables are independent, I can multiply this by sigma squared. Any function of this would be independent of any function of that. In particular, sigma squared times this would be independent of sigma squared times that. And that's the second conclusion of the theorem. Moreover, I know that 1 and then 2, that Q2 has a chi-squared distribution with, let's say, r degrees of freedom or r2 degrees of freedom, where r2 is just the rank of I minus HA. That's the degrees of freedom of this guy, minus the rank of I minus H. That's this guy. Okay. And then, and then we're going to go to the chat saying that the rank of I minus H is the dimension of LAX perp. That's right. So, another page here. So R2 is rank of I minus H. Repeat this here. Minus. So coming back here. Rank of I minus H. So this is the dimension, if you want, this is the dimension of the complementary space. So H of it is projecting onto that. This is going to be the dimension of LX perp. HA is projecting onto this, so I minus H is projecting to the orthogonal complement. Or you can just say that this is equal to, it's going to be n minus, in any way that you like want to do it, it's going to be this minus the rank of HA, in fact, because these are projection matrices. So remember the eigenvalues of this are zeros and ones. When I subtract I, the effect is that I like switch the zeros with ones. So when whatever was 0 in HA would be 1 for this, whatever was 1 for this would be 0 for this. I flip the, so the complementary, if you have two complementary projections, let's say one is like this, the complementary projection would have zeros here, ones here. The eigenvalues are just the opposite of each other. And the sum of the two would be just the identity. So this would be the number of non-zero elements, like eigenvalues of this would be n minus the number of non-zero, like eigenvalues of HA. And this is just the dimension of LA of x, which we at some point figured out would be, yeah, let me do it later. So this is going to be n minus rank of h, which is going to be the dimension of L of x. So we know that this is, at some point we figured this out, that what is the dimension of L of x? Anyone? Members. So we have L of x
P plus 1.
Yeah, p plus 1, or sometimes I write it as d. Yes, that's the number of parameters basically in the regression, or the number of columns of x. So how about the dimension of this restricted space? That's a little bit tricky, but what we have is, like, we have the regression and we impose q constraints, q independent constraints. So the number of free parameters that remain, which is going to be d minus q, that's going to be the dimension of LA of x. So that's basically the number of parameters of the restricted model. So then if you believe this, this would be basically d minus q minus d, which is going to be, minus, so n's cancel out, these two cancel out, and I get negative this plus d, I get q. So in the end of the day, once you do the calculation, the difference is just q. And you could have derived at this in different ways, but basically the difference between the rank of these two is the difference between the rank of the underlying subspaces. This is the same as basically the rank of HA minus the rank of H, or the difference dictated switched. So this is equal to, what we have shown here is that this is equal to the rank of H minus rank of HA as well. So once you divide cancel out n and so on. So this little calculation is a little bit tricky, but in the end, once you understand the dimension of these spaces, things would be like that. Okay? Questions? Any comments, questions? Is it more clear now, maybe? So there's a key step in the proof in which you have to argue that you can kill basically this mu when you apply these to y. And the mu is killed in both cases for both of these, because mu is in both of these subspaces. It's in the restricted subspace, which is also inside the bigger subspace. So there's no mu left. So if you work under the alternative, then this is not true. So this one, because this is not going to be there, you can't simplify this. So this is going to remain, and then the distribution of this guy is not going to be chi-squared. It would be non-central chi-squared because there's this shift in the mean, and so that's not what we're going to discuss. That's worth noting. So this result is only true under the null, and that's exactly what we need to set the threshold of the test and so on. Okay, sounds good. Okay, let me see if I can pull up. So that's all I want to talk about quadratic forms, and now we have a proof of this result. We didn't prove Cochran's. I'll see if I can give you proof, maybe. I haven't done this in this course, but let's see how it goes. I want to maybe pull up a, okay, I see a yes in the chat. So assuming that the yes is that everything is clear. So let me pull up, I'm going to discuss next something that's left from chapter 4, and then we'll be done with the chapter 4. So let me try to pull this up. Give me a second. Just want to set up the problem, and then we'll talk about this next time in more details. Okay, sorry, don't know why. Just give me a second. That's fine. Let me show this. These are annotated slides. Oh, sorry. Screen. Okay. So okay. So let's see. Right. So what I want to say is we're going to discuss this idea of optimality, and so we had the beta hat in the regression. You recall that this was like that, and this is a particular estimator of the coefficients. And we derived this using MLE, and we said that the MLE reduces the least squares problem and so on. The question remains whether this is a good estimator. Maybe there are other ways that you could drive an estimator and that would be better. So this idea of Gauss-Markov is that this estimator has some sort of an optimality property in the sense that it's best in a particular sense. And the Gauss-Markov so can be just stated in like mnemonic form as the LSE of beta is blue. Okay, so the least squares estimate is blue. What is blue? Blue is the best linear unbiased estimator. So among all the unbiased estimators, this is best. Best means has the smallest variance. Okay, so let's say the coordinates have the smallest possible variances. This is good because this shows that we can't improve. The variance is usually the, for unbiased estimators, the variance is the measure of performance because the mean of the distribution, the mean is correct for any unbiased. So we know that this is unbiased. Any other unbiased estimator, the expectation would be the same as the parameter. But the smaller the variance is, the more concentrated you're going to be close around your mean, which is the correct parameter. So the estimator has the correct mean, but it's going to be like beta hat would be like spread out around the true beta. And so the sharper this concentration around beta, the better. And it says this is saying that this estimator has the smallest possible variance. And that's the content of the Gauss-Markov theorem, which we're going to discuss in the next lecture. Okay, so that's this theorem. The statement is a little bit more elaborate. So I'll encourage you to go look at, I'm going to post these and go look at this from the previous lectures, the idea of Gauss-Markov. And then there is an application to generalize these to squares. And that's the main thing that we would like to cover next time. So have a look at these the videos that discuss these ideas, and hopefully we'll come back and talk about this next week. Okay, sounds good. Questions? Okay, if not, let's